now that we have a little bit of a review of oxidation and reduction under our belts, let's see if we can apply what we now maybe re-understand to cellular respiration. So cellular respiration, for every mole of glucose is C6H12O6. We combine that, maybe that's in an aqueous state, it's dissolved in water. We combine that with 6 moles of molecular oxygen, and then our cells perform cellular respiration in a whole series of steps, and I'll do more videos on that. It performs cellular respiration. I'll just abbreviate it. And then we end up with 6 moles of carbon dioxide. We have to breathe this oxygen in order to perform cellular respiration, and then we have to breathe this carbon dioxide out because this is a byproduct of cellular respiration. 6 moles of carbon dioxide, 6 moles of water, and then the whole point of cellular respiration is plus some energy. Some energy is generated by this reaction, and our bodies store this energy. Well, some of it is just turns into heat, but the whole point of cellular respiration is to store it as 38 ATPs, which we've learned already is the energy currency of biological systems. And then our bodies, or biological systems in general, can use these ATPs to contract muscles or generate nerve impulses or grow cells or divide cells or whatever else that a biological system has to do. In the last video, we learned a little bit about oxidation and reduction, so let's apply those ideas here. Now, we saw in the last video that a chemist would say, let me write it this way. A chemist would say that oxidation means losing electrons, or being able to hog them, not being able to hog them, losing electrons, while a chemist will tell you that reduction is gaining electrons. And if you need, if you have trouble remembering, oxidation is losing, that's kind of the oil, that's the mnemonic. Oxidation is losing electrons, and reduction is gaining, or rig. So oil rig. This is what you learn in chemistry class. Now, a biologist or biochemist will say, oh, well, I like to define a little bit different. So let me write this. A biologist will say that oxidation is losing hydrogen atoms. And they'll say reduction is gaining hydrogen atoms. And we saw in the last video that this definition is actually hard when you're actually applying it to hydrogen, because it's not like a hydrogen atom can lose itself or gain itself. And the reason why we said that these two ideas are consistent is because if I'm talking about a carbon, and a carbon is losing a hydrogen, so, let's say I have some compound that looks like this, maybe it's connected to a bunch of other things someplace else, and then later on the carbon, let's say I have carbon that looks like that, and then I have an oxygen that's maybe bound to another oxygen. I'm doing it very kind of a hand-wavy explanation here, and maybe that oxygen is bonded to something else. If this is what I start off with, and then on the other side of this equation, I end up with something that looks like this, where the carbon is bonded to an oxygen, and maybe that other oxygen is bonded to this hydrogen. The biologists say, oh, this carbon has been oxidized because it lost its hydrogen, right? The hydrogen went from here, I'm doing it in a different color, went from this carbon to this oxygen, and the biologist would also say that this oxygen has been reduced. It's been reduced because it gained hydrogens. But the reality, or maybe the chemist definition, which I like a little bit more, is over here, the carbon was, because carbon is more electronegative, right? We see carbon is much more electronegative than hydrogen, and oxygen is even more electronegative than carbon. When any of these guys bond with hydrogen, they're going to hog the electron. So here, carbon got to hog the electron. So here, carbon hogs electron. While here, carbon gets its electrons hogged by oxygen. So here, oxygen hogs. So by losing the hydrogen, the carbon actually lost its opportunity to hog electrons. And since it ended up bonding with an oxygen, it actually not only can't hog hydrogen's electrons, but then it gets its electrons hogged by an even more electronegative atom. So that's why these two definitions are consistent. Same thing with the oxygen. Here, it's bonding with another oxygen, not hogging anything. But when it gains the hydrogen, it's able to hog hydrogen's electrons because it's so much more electronegative, or you could say that it's gaining electrons. So that's why these two definitions are somewhat consistent, although sometimes they fall apart if we're not dealing with hydrogen. The chemistry definition applies more consistently to everything, but sometimes the biologist definition is easier to kind of glance at, or you'll actually see it written in textbooks. So let's go back to cellular respiration and try to figure out what's being oxidized and reduced. So if we look over here, well, we have our glucose, and actually I copied and pasted from Wikipedia a glucose molecule, and actually there's one error in here. Maybe I should edit it on Wikipedia. There should be another hydrogen bonded to that carbon right there. But as you see, all of the hydrogens, they're either bonded to a oxygen or a carbon over here, right? On the left-hand side, they're either bonded to an oxygen or a carbon. If we were to write its oxidation state, in every case, it's bonded to something that's more electronegative, so it's going to be giving up its electrons, so it'll have a +1 oxidation state. And oxygen, in every case, is either bonded to a carbon or a hydrogen. And so oxygen, if it's bonded to a carbon or a hydrogen, is going to hog an electron from either one of those guys. So in every situation on glucose, oxygen has a 2- or a -2 oxidation state. And carbon, since this whole thing is neutral, one would think that carbon would have a neutral oxidation state. And if you go through this, you'll actually find that most of these carbons do have neutral oxidation states. Let me circle a few. So for example, this carbon right here, it's hogging an electron from this hydrogen, but then it gets an electron hogged by this oxygen. And then, of course, it does nothing with the carbon, so that's neutral. This is neutral for the same reason. This is neutral for the same reason. This one is also neutral for the same reason. It's bonded with two carbons. It has an electron hogged by oxygen, but then it hogs an electron from hydrogen, so it's neutral. So 4 of these carbons are neutral. This carbon right here has 2 electrons hogged by oxygens, and then it gets to take one back from the hydrogen. So it has a +1 oxidation state. And then this one's the opposite. It has 2 hydrogens that it hogs from, then it has to give one away to the oxygen. So this has a -1. And so these two cancel out. So on average, you can say that the carbons in glucose have a neutral oxidation state. And I'm dealing with the chemist definition, and I'm going to show you that they're essentially equivalent. Here, all of the oxygens have no oxidation state because they're just bonded. Let me do it in a better color. No oxidation state, or neutral oxidation state, because they're double bonded with oxygen. No one's hogging from anyone. They're obviously equally electronegative. If we look at the products, carbon dioxide looks like this. So in either of these cases, this oxygen is hogging 2 electrons from this carbon. So it has a -2 oxidation state. This oxygen is hogging 2 electrons from carbon, so it has a -2 oxidation state. And this carbon is getting all of its valence electrons, all 4 hogged by the oxygen, so it has a +4 oxidation state. It's lost 4 electrons, you can imagine, because it's getting hogged. So that's carbon, so we could write this as 4 plus for the carbon, and then each oxygen has a 2 minus, and we can do the math later on to figure out what the total is. And then if we look at the water, and we've looked at this before, the oxygen is hogging 2 electrons from one from each hydrogen, so 2 minus, and then each of the hydrogens have a +1 oxidation state. So if you want to do a half reaction for cellular respiration, and that's in kind of the chemist sense of things, just dealing with electrons, you can immediately say that I start with 12 hydrogens. I start with 12 hydrogens on this side. Let me just write it this way. So H12 on this side, and they all have a +1 oxidation state, and then cellular respiration occurs, and now I have 12 hydrogens. I can write the 12 a little bit differently here, but they still have a +1. Each of them still has a +1 oxidation state, so nothing from an oxidation reduction point of view happens to the hydrogen. Now, if we do the carbon, on the left-hand side of the equation, we have 6 carbons. They have a neutral oxidation state, but then on the right-hand side of the equation, what happens? I now have 6 carbons, written a little bit differently, but I have 6 carbons, and they each have a +4 oxidation state, which means that they have lost 4 electrons, or their hypothetical charge by losing those 4 electrons has gone up by 4 because they're losing negatively charged atoms, or actually negatively charged electrons. So the carbon, the 6 carbons after cellular respiration end up with 6 oxidized carbons with +4 oxidation states, plus, so each of these lost 4 electrons. We have 6 of them. 4 times 6 is 24 electrons. These are the electrons that the carbon lost. So we see in cellular respiration that the carbon is oxidized. Carbon oxidized. Right? Oxidation is losing electrons. We see in cellular respiration, we draw the half reaction. Carbon is losing. The 6 carbons are losing a collective 24 electrons. And then finally, if I were to do the oxygen on this side, I've lost my equation up here. So over here, I have 2 oxygens, and I'm going to draw them a little bit separate. So I have these 6 oxygens here. I have these 6 oxygens here that have a -2 oxidation state on the left-hand side. So I'll draw it like this. They have a -2 oxidation state. And then I have these 12 oxygens that are completely neutral. And then I have, let me do that, those 12 oxygens that are completely neutral. So I won't even write an oxidation state or oxidation number there. And then after we perform cellular respiration, what happens? Well, now I have, in the carbon dioxide, I have 12 carbons that have a -2 oxidation state, right? 6 times O2. So let me write that down from the carbon dioxide. So I have 6 O2s that all have a 2- oxidation state. And then I have another 6 oxygens that have a -2 oxidation state. So plus 6 oxygens that have a -2 oxidation state. So if you think about it, over here I had a collective oxidation state on all of the oxygens. These were neutral. I have 6 times -2. That's a -12. You can kind of view it as collective charge of all 6 of them. 6 times -2. Here I have 6 times -2, which is -12. And then I have 6 times 2 oxygens per molecule. So that's 12 times -2. That's -24. So to go from a -12 to a total oxidation or kind of hypothetical charge of -36, I must have gained 24 electrons. And those 24 electrons that I gained, that the oxygens gained, are the same 24 electrons that the carbons lost. So from the chemistry point of view, it's very clear. Carbon was oxidized, and oxygen, which gained electrons, right? It's gaining these electrons right here. Reduction is gaining. Oxygen is reduced. And this is all a bit of review, but it's nice to see it in the context of cellular respiration. And this actually kind of answers one of the questions of where does this energy come from? Where does this energy come from? In any of these chemical reactions, when you see energy being produced, it's because electrons are going from a higher energy state to a lower energy state, right? If I have an electron that's up here at a high energy state, high, and it is able to go to a more comfortable state, a lower orbital, a lower energy orbital, so low energy or more stable energy state, it'll generate energy in the form of heat, or maybe this can do some work in some way, help make ATP molecules. And so when you see these half reactions, you see these 24 electrons that are being lost by carbon. Carbon is being oxidized, and they're going to oxygen. They're going in a whole series of steps. It's not just happening in kind of one huge explosion. It's happening over a huge series of steps. And as it does that, it's entering lower and lower energy states. And as these electrons enter the lower energy states, essentially by going from the carbons and being pushed to the oxygens, that's where the energy is coming from. That's where the energy to make the 38 ATPs is coming from. So far we talked a little bit about how a chemist views oxidation. I touched in the beginning of the video of how a biologist views oxidation. And then we saw that cellular respiration from a chemist's point of view is clearly showing that the carbon is being oxidized. It's losing electrons. And that the oxygen is being reduced. It's gaining electrons. It's being reduced. That the electrons are going from this carbon, and they're going essentially to these oxygens right here. Now, how does the biology definition of oxidation hold up? Well, here it holds up pretty well. Because you can imagine over here, all of the hydrogens in the equation are associated with glucose, right? And so they're either bonded, if you actually look at the structure of glucose, the hydrogens are either bonded to carbons or oxygens, right? So these are bonded to carbons and oxygens. But when you go on the right-hand side of the equation, all of the hydrogens are only bonding with oxygen. So net, carbon definitely lost hydrogens, and hydrogens and oxygen definitely gained hydrogens. Let me write that down. We see in respiration, carbon lost hydrogens, and oxygen gained hydrogens. And that's consistent because we see that by losing hydrogens, we are being oxidized from a biologist's point of view, and by gaining hydrogens, oxygen is being reduced. And just so you can kind of make sense of this, when you see this in, when I start drawing out the mechanisms, which I will hopefully not make too hairy, this process of transferring these hydrogens is facilitated by molecules like NAD plus and FAD. And we'll see that. But it's really, if we just want to reconcile the two notions, as the hydrogens are being transferred from one electronegative atom to another electronegative atom, what's really being transferred is the opportunity to hog electrons. If carbon has a hydrogen, it gets to hog the electrons. But then if that hydrogen goes from the carbon, and the whole atom, not just the nucleus, the whole atom goes to the oxygen, now the oxygen has gained that electron that it can hog, and carbon has lost the electron. So carbon has been oxidized, and oxygen has been reduced. And I've mentioned this in previous videos, but probably the most confusing thing about oxidation is that you always want to say, hey, that must have something to do with oxygen, and it does. The word really comes from what would oxygen do to something. So oxygen, when it bonds with things, it takes away their electrons. Or in a reaction, it'll often take away the hydrogens. It took away the hydrogens from the carbon in this situation. So that's where the term oxidation comes from. But you don't have to have oxygen anywhere in your reaction for oxidation or reduction to occur. Anyway, hopefully you found that reasonably useful. This was actually a huge pain point for me when, I got comfortable with the chemistry definition of oxidation reduction, and then all of a sudden you open up your biology book and they start talking about losing and gaining hydrogens as opposed to electrons, and it took me a while to really reconcile these two notions.